All right. Bill just was talking about EA 19-inch and how old it is, 1922, I think. I wonder if, what we talk about today and how we're evolving our rack architectures, how it's going to be seen by our grandkids and great-grandchildren. I wonder if there'll be another forum like that here 40, 50 years from now when people are talking about the rack architecture. I hope so. It's a sign of good engineering, which I think is awesome. So I'm going to talk about Open 19 technology. Just as a brief, we recently contributed a Open 19 technology from LinkedIn to OCP. It is right now in the incubation committee. If you're in the Bay Area, I think mid-July, there's going to be a discussion around the architecture in more depth. So please feel free to join. And so we are hoping that this technology gets adopted to a much wider community other than what we've been doing at our data centers in LinkedIn. So I'm going to talk about the architecture in a lot more depth. So just to give you some idea of why we were motivated to do this, years back, we were working at our data center with some constraints. We were constrained a lot by space and obviously power. So we didn't have the luxury of saying, hey, I'm just going to buy a lot of land and just plow through a lot of racks, and I don't care, each rack can be 9 kW. We actually had some constraints where we had to maximize our space and power. So in order to do that, we wanted to pack as much compute as possible on a rack. So our motivation came around the fact that we wanted to have an array of compute up to 96 servers per rack. And in order to do that, we realized that as we scale, the complexity will require us to come up with something new, especially when we want to hit some of the economies of scale. We want to increase the efficiency and drive down the cost. So in order to do that, we came up with this Open 19 technology, and the basis of the technology is that it's based on what's called a brick cage, which is basically the form factor definition that fits into any 19-inch rack, because we always had 19-inch racks only. And the idea was that you could pick a sushi menu of servers and put it into this brick cage in many configurations. You could do a double high brick, a double wide brick, a brick, which I will go into detail in the next few slides. And we wanted to remove all the power components from the individual compute nodes, so we built a power shelf. And then the other major component in this rack architecture was the switch. So in this diagram, you see 2 switches. That's very unique to our environment. You don't have to have 2 switches per rack. We at LinkedIn kind of designed it so that we have what's called leaf nodes. So a rack has 2 leaf nodes, but it's single top of rack. It's just that the way we sort of configure it inside the rack. So this is the sort of the overall sort of design, and now I'll go into a little bit more depth. So the brick cage, the component I talked about, it's a very passive cage, and it comes in 2 options, in 12 RU and 8 RU, and you can fit, as you can see on the left side, 4 times the breaks. You can double high, you can go double wide, and so you can kind of take out sleds in between and decide, okay, I'm going to fit a much larger server, or I'm going to fit a much, much smaller break. And the idea was that it could give us the ability to put a wide variety of compute without having to waste the space inside the rack. And the back component, as you can see on the right side, is all snap-on cabling using blind mate connectivity. And so that way, as Bill was showing in the Olympus design, it's very sort of same concept, where we just don't want the data center technicians to go in the back and having to do a lot of work. We just want everything just slide and snap on. The idea is that the data center technician should not have any screws or anything like that. You just want them to use their hands and easily slide things in and out. So now we can talk about the form factors that actually go into those bricks. So as I was saying, there's a brick, and these are all, by the way, compute nodes that we requested all manufacturers to build. We don't want to design all these servers by ourselves. We want to open the architecture in such a way that you just have to think about the blind mate connectivity in the back and snapping on inside of the server. It can just stay the way it is, and multiple vendors can sort of build that as long as you're building it to sort of these specifications, which is brick. You can build a double wide brick, double high, and also the half width bridge. And as you can see, they have a linear power and data, and they're self-sustained. It's all EMI tested and safety, and they all are connecting to 100 gig blind mate network. Now, this is where I find great joy in this. This part here was one of the biggest innovations we did. We thought, you know, one of the things we really, really hated inside the data center was the complex cabling that comes with it. I'm sure all of you have experienced the same thing. So we decided to really put a lot of emphasis here and double down on the blind mate connectivity design. And as you can see here, all your cabling in the back is disappeared, and everything is on the blue cable, on the blue shielding is the power, and the white is the network. And so they're snap-on in the back, and the network is switches are 25 gig components, so they're all 100 gig, 25 each snap-on is 25 gig, and they all are designed for the 100 gig platform. And the idea is that they're extremely easy to manage, and like I said earlier, you know, again, we don't want data center technicians to be spending a lot of time cabling or dealing with screws. So the whole idea was that we could actually do this a lot faster. We've actually seen, you know, somewhere up to orders of 6x improvement in rack integration just by using this design. So it's really served our purpose really well. So let's go into the power shelf, which is the sort of the next phase. Now, this is interesting. We took out all the power components from inside the server, and everything connects via the blind mate all the way up to the power shelf. The power shelf can do 19.2 kW because we want to really dense up our compute. It's 1 RU, very, very small real estate needed onto the rack. Its management is via BMC. We use Open BMC as well, and so all of that can be completely managed. And we wanted the ability to all the servers to be singly managed, and we can turn on and off all through the power shelf. So that's really served us well. And it's fully redundant. It's got separate A and B inputs, and we're working with multiple vendors on this as well. So we'll talk about some of the benefits. One thing I actually wanted to talk about as a benefit that's not here is that that just came out of accident. A lot of people here have been talking about edge and why and what's really needed on the edge is a different type of support. A lot of the racks that are going into the edge are you know, not going to be maintained by the same data center technicians. You want the edge racks to be completely easily managed, self-managed, very low touch. So we actually have been talking to a lot of people who've been finding use case for Open19 to be on the edge, because once you just clip everything, you touch it, you know, less chances of cable going mismanaged and all those. So that has been actually a very interesting use case for us, and we're finding that there are some people that are interested in adopting that. So I just wanted to call out that that's one benefit that we're seeing in the industry that I'm not calling out here, but it's been interesting. So the idea is that this absolutely fits in any 19-inch rack. We actually at LinkedIn have a 19-inch rack where we do water side economization. So we actually bring water into the rack, we cool it, and our architecture like fits right into it. So we can cool the racks with water plus with this technology platform. And we've seen, you know, like I said, 5 to 6x rack integration real fast. If you go on YouTube, you'll see my presentation that I did at OCP, and we had a video of a normal size rack integration and an Open 19, and you can actually see how fast it is. Unfortunately, I couldn't bring the video here, but you can go see it on YouTube. The redundancy, AB to N power. There's no central controllers, and you can monitor each server separately, all by the BMC module that we have. So on the server side, we increase efficiency by having no power supplies, and we conserve a lot of power this way and make our rack entirely efficient. We're finding a lot of savings on this. As we are scaling our data centers, we have thousands of these now, and the savings are pretty big. So that was one of our sort of motivations of doing this as well. So I wanted to show you what it looks like in our production environment. On the right side is just empty cages, servers ready to be put in. So these are rows in our Oregon data center, and then on the right is actual compute nodes where the form factor fits in, and you can see how easy it is to slide them in. And it just looks like a regular 19-inch from the outside. But as you can see on the top there's some space. You can see how it snaps on. So the other thing I wanted to call out was a very interesting situation we came in. We were looking for high-end servers for high memory. So one thing that LinkedIn does is we build the economic graph. The economic graph is a very complex application. It requires tons of memory. So we have this project called Liquid, and it takes it consumes 3 terabytes of memory per server. It's humongous. And so we were trying to find, okay, how do we find the right architecture for this? And since we were part of OCP, we just sort of went into the community and said, oh, I think the Olympus motherboard will be the best fit. So we took the Olympus motherboard and actually put it onto the Open 19 platform. And all these blue servers in our data center are actually the Olympus motherboards that are serving a high memory application. And so I wanted to show you how that view looked like. So we can take, the beauty about this is that we can take other things and integrate it into Open 19 as well. And I think the combination of what we did at OCP with Olympus and Open 19 has been sort of a true testament of what Bill was saying earlier about how we are sort of converging and bringing things together. So this is sort of one of the early examples of that that I'm extremely proud of. So I wanted to share that. So in the future, we are open to looking at different cage form factors. We're just in the very early stages. We are actually putting some new server modules. You'll see in the future, LinkedIn will be contributing some of our own server architecture and opening it up. So that's sort of in our roadmap. So I wanted to talk about it. And potentially we're going to be working with the different ICs and maybe look into the edge as well and see if there's any convergence there that we can do on those platforms. That's an example of a cabling system in the back. Actually, I wanted to show that you can see how it is running in production. So it's all very neat and clean. All right. Oops, I went too far, I think. That was actually my end of my slide. Sorry, it's doubled. All right. Thank you very much. I hope this was very informational. And if you have any questions, I'll be around most of the afternoon. Please feel free to ask. Shishia.
So Zaid, real quick.
Yes.
You guys had an event in Santa Clara recently. There was a rack sitting out, and there was a challenge. How fast can you assemble this complete rack and all the cabling? Did you know what the final number was?
You know, I'm trying to remember. It was on the order of minutes, right? Like
yeah,
30,
I think it was.
20,
I think it was
to,
2.5 minutes.
Yeah, 2.5 minutes.
So
it was like super fast.
He talks about ease of use, and I literally saw that in person.
Yeah.
There were a challenge, and people were just literally attending this conference, walking up, and they could completely populate the rack with compute nodes, install all the cables, and it was 2.5 minutes to do it.
Yeah.
So I think when you said a 6x improvement,
Yeah.
I think that's an understatement.
It could be. We're trying to be conservative, but
Yeah,
because, it depends on the folks in there.
Lots
but
of
absolutely.
good technology there.
Thank you.
So
Yeah,
again, thank you.
Yeah.